My name is Andrew Nassief, and I will be going over toxin detection methods and signal efficiency. So I will be talking about the various telemetry protocols and networks and peer-to-peer syndicated protocols that my startup, Stark Drones, works on. So next slide. So brief introduction. So in the past, I have built variations of underwater wireless sensory networks in order to collect real-time data about oceanic contamination. This time, I propose another real-time sensory network that utilizes various upgraded telemetry techniques, such as an extra data syncing peer in order to improve the data collection process. I'll then be comparing it to data from my previous sensory networks and contrast it with the timing and data of traditional wet and chemical methods, meaning non-peripheral devices through a series of experimentation. This is stuff that I've done in the past. Just talking about like my original thesis in terms of like what I've done. Bicep set out to prove that data syncing peer with signal conversion for a telemetry network can be algorithmically optimized in order to improve data latency for collecting real-time contamination data. Next slide. So today's topics are going to go over the core problem, the cost, current solutions that I've utilized that I'm currently utilizing, and then my previous solution, data extraction methods, the upgraded solution, meaning the solution for the future, what I learned, and conclusions so far. So next point. So the problem. So the problem that we are trying to tackle is mainly contamination in the water. Obviously, can cause serious danger. There are also different variations of like flesh-eating bacteria, brain parasites, and also stuff like detecting different phosphorus run-ons can help protect our lake. Another problem is in regards to timing. So timing and the collection of data is key. Every minute counts, and things such as chemical or wet testing methods can take 24 to 48 hours just for beaches alone. There's also a higher risk or margin of error in regards to potential human error, especially if you're dealing with chemical or wet testing methods. Not only this, but you have to an example is beach water testing. So I'm just using beach water testing in this slide as an example over oceanic testing. But for beach water testing, for example, you have to be closed for 24 to 48 hours, and the data might not be as useful for large-scale projects. Things such as detecting areas for potential mineral offloading can also benefit people much more with real-time or faster data. Next slide. So here are two key metrics that I noticed. So some testing methods cost over $30,000 in regards to wet and chemical testing. That's a lot of times out of your taxpayer dollars. And according to the WHO, 485,000 deaths per year come from lack of clean drinking water. So lowering the cost of detection dramatically can also benefit third world countries that might not have access to different sanitation devices that we have here, and as a result also don't have access to as expensive testing methods that we would have here. Next slide. And then another important fact is that more than 80% of our ocean is unmapped, unobserved, and unexplored. So obviously cheaper detection methods in terms of even like data syndication would also help with different things like different mapping technologies would be able to utilize a cheaper detection method as well as a cheaper data syndication method, especially when you're looking at things like the cost of sonar conversion and the different servers that have to do with software-defined networking and things like that. So next slide. And then obviously 70% of our planet's surface is covered by ocean. So oceanic preservation is very important. Once you have something like a cheaper detection method and you have all these wireless technologies that are also upgraded and cost efficient, then you're able to better detect different areas for like mineral offloading and oceanic cleanup. And it all starts with the detection. So I think the Toxin and the technology related to the Toxin is core. Next slide. So my previous solutions. So in terms of past sensory methods that I've deployed, and I'll get into like the different sensors in the next upcoming slides, the costs were much lower compared to the competitors. This includes for even optical and physical testing sensors. Part of this is not just in regards to like the optics involved in terms of like the optical engineering and nanoelectronics that involve to make such sensors, but also the different data syndication methods and algorithms. Like we essentially didn't just create a new sensor, but we also created a new wireless and telemetry method. And the cost alone for our standard devices is only $125 to $150 in parts for a device that is able to extract real-time data. And there are various metrics in regards to different charge cycles, how many times a sensor can be deployed, and also the radius of the detection. But that $125 to $150 is very comparable in regards to the same efficiency of sensors that cost upwards of $15,000 or more, and even compete with some of the $30,000 sensory methods. In regards to prototypes, the first solution I built, it had a problem with the enclosure design and the deployment. The secondary solution I built fixed the enclosure and also optimized the signal processing method for more optimized like sonar conversion. And then in regards to the data, the signal strength was in real time for underwater detection, and the results allowed for higher data extraction efficiency. And tests so far have been basic lake deployments for previous solutions. So we've done limited lab testings as well as deployment in places like Harbor Beach, as well as various different lakes. Obviously, we'd be able to do more large-scale testing if we had more funding, given the places we're allowed to go in regards to the deployment and the resources we have to get there. Next slide. So there have been various iterations of prototyping and R&D. The first prototype is the one with the green rope on the right-hand corner, and then the next were for different upcoming phases. And as you can see, certain designs improved. So there is a design for even the networking architecture. So the network architecture is a peer-to-peer data offloading module that utilizes our wireless networking protocol. And it's basically almost as if we designed a custom modem that connects to the sensors that collect real-time data. And people haven't thought of like mesh networking approaches or peer-to-peer data syncing approaches for things like that. So the options in order to release something new into the market in terms of like networking efficiency and actually different methods that could improve like even current acoustic networks is there with the modules that we created. Next slide. So in terms of attention this got so far, we've got some attention from the Department of Energy and Environment. We also presented in Gigabit DCX and MakerVare. And basically, the presentation is centered around our ability to create underwater wireless sensory networks that can track information about our waterways utilizing noiseless signals, which is very important because obviously, given the Doppler effect in water and things like that, you're not going to be able to have traditional networks. And even with the acoustic networks that utilize sonar conversion, since they don't have an architecture that is centered around mesh networking or peer-to-peer data offloading, they utilize usually expensive servers, and it's a software-defined networking approach that's very centralized, and the amount of modules that need to be deployed and stuff like that and the cost up front is much higher. So really we're trying to optimize costs in relation to not just the sensors, but also the networking aspect to it, as well as the data collection aspect to it, especially in regards to like real-time data collection buoys. Next slide. So in regards to the current solution, as I said, the more advanced solution is centered around P2P sensory networks for further expanding the data syncing through a mesh-like architecture. There are further advancements in regards to hardware prototypes and even things such as hydroelectric wireless grid implementations. For sake of simplicity, the focus now in the beginning is to just focus on networking solutions, which will include even things such as controlling power up and usage. So things like the deep sleep protocol or controlling when a sensor turns on and off and things like that are other algorithmic optimizations that could be done in the future. Next slide. So we're utilizing our own hardware design. It's through one of my startups. It's called Saneboard. It is a wireless P2P networking development board, and it also has a built-in LoRaWAN gateway, and it has different lightweight MCU modules that is uploaded with our custom firmware in order to sort of work for the different like modems and routers that we're trying to create. So we have our own complex PCB designs that have lightweight MCUs and LoRaWAN gateways and things like that. And this is just version 1. The next upcoming versions, once we get access to higher quality manufacturing, it would be much more lightweight and robust. Next slide. Okay, so regarding importance, questions regarding data collection and targeting. So there's a debate in regards to collecting nitrate levels versus phosphorus run-ons. We believe tackling both is key, and the way you could do that is not just with the data collection method, but also things like optical mass spectrometry also plays a huge role in being able to do that, and the software-defined networking capabilities that we are either integrating with our optical peripherals or upgrading through the various P2P and mesh networking modules that we are working on. And as mentioned previously, this allows you to focus on the data retrieval in real time while detecting various different toxins and other problems that occur. You may even integrate detection with third-party software and dashboards. Next slide. So results. So what I've learned so far in regards to creating these different networking modules and these different sensory mechanisms is signal strength and processing. So we can offload signal data and networking caches through P2P networking. Compared to others, this allows us to be better suited for optimization as compared to many underwater acoustic networks. We integrate different communication protocols which we developed. And then in regards to power up module, things like deep sleep or our own power up optimization method also helps in regards to when sensors are not collecting data, then we're able to basically set them off, or we're able to turn them on at certain times to optimize its efficiency. Next slide, please. Okay, so last slide is going to be the sources. So this were just in relation to like the various facts that we had on our website on our slides, and then oceancolonization.com and starkdrones.org is my website. And yeah, that's the presentation.